AP Stats. Hope you guys are having a great day. Today we're moving on to 3.2.2. This is the second day of 3.2. There's actually 4 days that we're going to spend on the section 2 of chapter 3. This is about the least squares regression line and what residuals are, and then how they're related. So one, we're going to go over what residuals are and what they are in context. We'll talk about what least squares actually means in terms of the least squares regression line. Use technology to find a least squares regression line. We kind of did that in the last video, so I don't think I'm going to spend a lot of time going over it. And then finding the slope and intercept of the least squares regression line from the mean standard deviations of x and y and their correlation. Oh my god, that's so much stuff, and you have no idea what I'm talking about, probably. That's okay, because you will by the end of the lesson, so that's cool. Alright, so I'm going to kind of jump around a little bit. I'll do a definition and then show you an example and then kind of jump back and forth a little bit. So just to let you know that that's coming. So a residual is something that measures how far off the line of best fit predicts an actual observation. Okay, so the formal definition is that it's the difference between an observed value of the response variable. Response, remember, is the y, and the value predicted by the least squares regression line. Okay, and so to calculate the residual, you need to do the actual y minus the predicted y. And so if you ever have trouble forgetting that it's actual minus predicted, it is AP, which is the class that we're in. We're in AP, so it's actual minus predicted. It's also my name. So if you remember notation, okay, so your residual is your actual y minus the predicted y. Remember, the actual y is just y, and the predicted y is y hat. So I can write it like that as well, y minus y hat, or a minus p. AP, because we're in an AP class. So don't forget, a minus p, not p minus a. Pa. A minus p. AP. Okay, so that is what a residual is. Super easy to find, right? Because if you have the observed value minus the predicted value, then you just subtract the two numbers. So math isn't that hard. However, conceptually, I just want to kind of show you what that actually is. So here's a graph. So this is the body weight of a hiker versus the pack weight that they can carry. So in theory, it should be a positive correlation because the heavier you are, the more you should be able to carry. So these little black lines here are the residuals, okay? So you have your observed value, which is right there, and then your line of best fit would predict where the x is, and so your residual is that y value minus the y value that's predicted by the line of best fit. So all of those lines there are the residuals. Okay, so yes, try this example first. So find and interpret the residual in context for a hiker who weighed 187 pounds. So go ahead, try that, and then I will show you the answer and explain. Okay, so your residual is your actual y minus your predicted y. So first we need to find the actual and predicted. So the actual is about 30 pounds, so that's going to be where that dot was. That's the observed value. And so here's your 187 body weight, okay, 187 pounds. And then you just kind of go over to the y-axis and find that that's about 30 pounds of weight on your backpack. And so the pink is the actual, right? Now the line of best fit, least squares regression line, is here, right? That line that's drawn in. And then here would be your prediction using the line of best fit. And so the blue is where you are going to expect your prediction to be. So you got to find, it's going to be around 33. But you have to actually calculate it. So using the least squares regression line, so this y hat equals 16.3 plus 0.0908x, right? That is the predicted pack weight is equal to 16.3 plus 0.09 times their body weight. So you want to plug in the body weight of 187 in order to get your predicted y. So here's your line best fit. Your pack weight, predicted pack weight is 16.3. Plug in your 187, you get about 33.28 pounds. Okay, so your residual is the actual, which is 30, minus the 33.28. So your residual is negative 3.28, and basically what that means is that the regression line over-predicted the hiker's backpack weight by 3.28 pounds. So basically they're a pansy and they didn't carry their full weight, the responsibility for the team. So they failed epically. Speaking of epic fail hikes, you should watch this. I think she was carrying too much weight. Whoops. Okay, so back to the least squares regression line. So more formally, now that we know what a residual is, the least squares regression line actually minimizes, okay, it's the line that makes as small as possible the sum, add them all up, of the squares, square them, of the residuals. Okay, so basically what that means is if I take the line of best fit, okay, so for example, our line from earlier, and I create the actual line of best fit, what's going to happen is if I take this residual and I square it, which means literally make it a square, find the area of that, so that's A1, and then do that again for this residual, that's A2, okay? So basically you're adding up all of the squares of the residuals and making that number as small as humanly possible, okay? And so that is where least squares comes from with the least squares regression line. Okay, so it might help if you kind of see this in action. So here's a scatter plot, and if I create, I don't know, a guess for where the line of best fit is going to be, my least squares regression line. So I plug in, okay, here's my line. I want to move it around so that I get closer to what I think is a good least squares regression line. So here's like my line of best fit. And if you look at, okay, these lines are the residuals, and what we're really curious about is the residuals squared, and so we want to minimize this area. So this number here, 197.34, is the sum of all of these areas, okay, and the square of the residuals. So if I move my line, I want to try to make this smaller. So if I move it around a little bit, okay, 199, it's going up, See, those boxes are getting bigger. And so I want to continue to try to make it as small as possible. So I think probably the smallest I can get right now is like around 191. Now if you look at the actual regression line, that is pretty close. The residual squared is 163, so I still haven't minimized the area yet. So anyways, that's the sum of the squares so that you can be aware of the exact what a least squares means in the least squares regression line. So hopefully that helps. Also, if you want to play around with this app, it's rossmanchance.com/applets/reg. So if you want to kind of just like mess around with it, you're welcome to. Okay, so back to our definitions. Least squared regression line, more formally, is the line that makes the sum of the squares of the residuals as small as possible. Okay, so the least squares regression line is very, obviously, very closely related to the residuals. And so there's actually a way to get the least squares regression line without using the data. The formulas I'm about to give you are actually on your formula sheet, so you don't need to have them memorized, but you do need to know how to use them and what they are and how it's all related. So the least squares regression line without data. So say, for example, you have a least squares regression line of the form y hat equals a plus bx. B in this case, which is the slope, is actually equal to, here's the crazy part, it's actually equal to r, the correlation coefficient, times the standard deviation of y divided by the standard deviation of the x's. So s sub y over s sub x. So if you were to, say, have the standard deviation of the y values and the standard deviation of the x values, and the correlation coefficient r, you could find the slope of the least squares regression line. Okay, again, this is on your packet, so you don't need to memorize it. The other thing that will help you as well is that a, which is the y-intercept, is equal to y hat minus b times x, or sorry, not y hat, y bar minus b times x bar, where y and x, y bar and x bar, are the mean of the y's and then the mean of the x's. So if you have like the stats, the numerical stats for the data, you can still find the least squares regression line. Okay, also super important, the least squares regression line always goes through the point x bar, y bar. Okay, so x bar is the mean of the x's, y bar is the mean of the y's. The least squares regression line will always go through the point x bar, y bar. So I'm going to kind of show you a little sketch of that and what that means. So if you go down to the other half of the notes, so this is kind of complicated. There's a lot of lines and everything, but kind of like it's good if you can like kind of understand this concept. Okay, so here the black line that I'm highlighting in blue right now, okay, that's the least squares regression line. This is for the backpack weight. Okay. Okay, I highlighted in black, so I'm continuing to color code. Okay, so that's the least squares regression line. And if you look at it, right, the purple line there, that is the mean body weight. So if I were to take all the hikers and add up all their weights and divide by how many there are, it would come up with whatever this value is, so probably about 138 or so. Okay. And notice that that goes through the line of best fit, okay? And then also I have this blue line, which is the mean y, which is the mean pack weight. So if I took all the pack weights, add them all up, divide by how many there are, I would get this value, which is approximately 29, okay? And notice that it does go through, that point there is x bar, y bar. And it does, it is on the line of best fit. Okay, so anyways, the rest of the lines are just kind of showing you how this relationship is set up. So you've got your slope, which is this height here, and then how much you go over. So this, what you go over is actually x bar plus a standard deviation. And then to your rise is kind of what we're is that ratio of r times the standard deviation of y. So this red value here is the mean of the y's plus the standard deviation of y's. So it goes, the slope goes over the standard deviation and goes up r times the standard deviation of y. And so that's kind of that the relationship there, and why you have this formula, this r times s sub y over s sub x, okay, because you go over s sub x and you go up r times s sub y to get the slope of the line of best fit. Okay, so here's an example to use those formulas. So you have the number of miles driven in thousands for 11 used Hondas have a mean of 50.5, standard deviation of 19.3. The advertised prices has a mean of 14,000 and a standard deviation of 1900. The correlation for these variables is r equals 0.874. Find the equation of the least squares regression line and explain what change in price we'd expect for an additional 19.3 thousand miles. Go ahead, pause, try it, and then I will go. Okay, so this is the answer to the first part. Y, so your least squares regression line y hat equals a plus bx. And then I define my variables. B is r times s of y over s of x, which is negative 0.874 over 1899 over 19.3 equals negative 86. and then you use the same formula for A, you get 18,768, so this is your line of best fit. Now the interpretation is a little bit more challenging, but they're asking for each additional 19.3 thousand miles, so here's your 19.3. Here's your interpretation. For every 19.3 thousand miles driven, we expect the car to depreciate by 1650.